This resource considers the student's t-distribution. We consider the reasoning behind this family of distributions that provide insight on populations based on small sample sizes. We look at how to find t-values from measured data. We delve into finding a more realistic confidence interval for a population mean by finding a critical t-value to supplement the mean and standard deviation from a sample. We discover how to find this critical t-value. We finish by looking at an example in its entirety. In the resource focused on confidence intervals, we realized that a larger sample size resulted in a narrower confidence interval for the population mean. However, a normal distribution is not always an optimal approximation for modeling a population mean. With the normal approximation, we also made a major assumption, that we knew the population standard deviation. Even if we do not know the population standard deviation, we would often assume it to be equal to the sample standard deviation. For large sample sizes, this is actually fairly accurate. But what happens when the sample size is smaller? Smaller sample sizes result in a family of curves that are similar to the normal curve in that they are bell-shaped and symmetric. However, the graphs for t-distributions have longer tails to account for the additional uncertainty inherent in the smaller sample sizes. But what exactly does this t-distribution look like? Much like the z-score for a normal distribution, we can find a t-score based on the population mean and the sample mean divided by the standard error. The standard error is the sample standard deviation, but it is adjusted to account for the smaller sample size. This is done by dividing by the square root of the sample size. Therefore, the smaller the sample size, the larger the standard error. The t-distribution is also subject to one additional parameter, the degrees of freedom. The degrees of freedom is found by subtracting 1 from the sample size. The idea of degrees of freedom is that the members of a sample will be closer to the sample mean rather than the population mean. This causes the standard deviation when compared to the population mean to be larger than when compared with the sample mean. When calculating the sample standard deviation, we divide by n minus 1 instead of just n. So how do we create a confidence interval using t-scores? Our small sample confidence interval for the population mean mu will be the sample mean x bar plus or minus a critical t-value multiplied by the standard error. As mentioned previously, the standard error is the sample standard deviation s divided by the square root of the sample size n. Also, the critical t-value depends on certain factors: the desired confidence level and the number of degrees of freedom. A link to a table of values to help find the critical t-values is provided. But how do we use the table to find the critical t-values? To read a critical t-value table, first we need to find the percentage of the total area under the curve present in the tails of the graph. As with the normal approximation, this area is equal to 1 minus the desired confidence level. With t-value tables, however, we must make an important distinction. Do we want an upper and lower bound for our interval, or does the situation only call for one bound? If the interval is bounded on both sides, we consider the two-tail percentage. If there is only an upper or a lower bound, we use the one-tail percentage. Next, we need to determine the appropriate rho, which is the number of degrees of freedom. Recall that the degrees of freedom is 1 less than the sample size. We can then find our critical t-value by finding the intersection of the row and column. Now that we have seen the general process, let's look at an example. Suppose we are curious to know the average weight of 10-week-old kittens. We want to build a 95% confidence interval for this population mean. To set up this confidence interval, we take a sample of 10 10-week-old kittens and weigh them. We find the weights to be 22, 27, 25, 20, 21, 31, 18, 22, 24, and 26 ounces. First, we have to find the mean of the sample. We add all the weights and then divide by 10, since we had a sample size of 10. The mean of our sample is 23.6. Now, we need to find our sample standard deviation. The general formula is that the sample standard deviation S is equal to the square root of the sum of the squares of the measured values minus the sample mean, divided by the sample size minus 1. The easiest way to do so is to work through the calculations step by step in a table. First, we subtract the sample mean from each of the measured weights. Note that the total of these deviations is 0. We square those amounts. Then we total those squared amounts and get 130.4. So our sample standard deviation is the square root of 130.4 divided by the quantity 10 minus 1, which is 3.81. Now that we know all our values, we can set up our confidence interval. Actually, we still need to find our critical t-value. We want to have 95% confidence, so we will allow for 5% error. We want to have a minimum and maximum for the interval, so we will look at the two tail percentages. Since we have 10 sample values, we have 9 degrees of freedom. Looking at our t-value table, our critical t-value for 5% error with 9 degrees of freedom is 2.262. Plugging in all our values, we find that the population mean is equal to 23.6 plus or minus 2.262 multiplied by 3.81 divided by the square root of 10. Performing the calculations and rearranging, this means that we are 95% confident that the average weight for 10-week-old kittens is somewhere between 20.87 and 26.33 ounces.